General-purpose computing on graphics processing units is the use of a graphics processing unit, which typically handles computation only for computer graphics, to perform computation in applications traditionally handled by the central processing unit. The use of multiple graphics cards in one computer, or large numbers of graphics chips, further parallelizes the already parallel nature of graphics processing. In addition, even a single GPU-CPU framework provides advantages that multiple CPUs on their own do not offer due to the specialization in each chip. Essentially, a Gpgpu pipeline is a kind of parallel processing between one or more GPUs and CPUs that analyzes data as if it were an image or other graphic form. While GPUs generally operate at lower frequencies, they usually have many times more cores to make up for it and can, thus, operate on pictures and graphical data effectively much faster, dozens or even hundreds of times faster than a traditional CPU. Migrating data into graphical form and then using the GPU to look at it and analyze it can result in profound speedup. Gpgpu pipelines developed out of scientific computing. History: general-purpose computing on GPUs only became practical and popular after circa 2001, with the advent of both programmable shaders and floating-point support on graphics processors. In particular, problems involving matrices and/or vectors, especially 2, 3, or 4-dimensional vectors, were easy to translate to a GPU, which acts with native speed and support on those types. The scientific computing community's experiments with the new hardware started with a matrix multiplication routine. One of the first common scientific programs to run faster on GPUs than CPUs was an implementation of LU factorization. These early efforts to use GPUs as general-purpose processors required reformulating computational problems in terms of graphics primitives, as supported by the two major APIs for graphics processors, Opencl and DirectX. This cumbersome translation was obviated by the advent of general-purpose programming languages and APIs such as RapidMind, Brook and Accelerator. These were followed by NVIDIA's CUDA, which allowed programmers to ignore the underlying graphical concepts in favor of more common high-performance computing concepts. Newer, hardware vendor-independent offerings include Microsoft's Direct Compute and Apple Chronos Group's Opencl. This means that modern Gpgpu pipelines can act on any big data operation and leverage the speed of a GPU without requiring full and explicit conversion of the data to a graphical form. Implementations: any language that allows the code running on the CPU to poll a GPU shader for return values, can create a Gpgpu framework. Opencl is the currently dominant open general-purpose GPU computing language, and is an open standard defined by the Chronos Group. Opencl provides a cross-platform Gpgpu platform that additionally supports data parallel compute on CPUs. Opencl is actively supported on Intel, AMD, NVIDIA and ARM platforms. The dominant proprietary framework is NVIDIA CUDA. NVIDIA launched CUDA in 2006, an SDK and API that allows using the C programming language to code algorithms for execution on GeForce 8 series GPUs. Programming standards for parallel computing include Opencl, OpenACC and OpenHMPP. Mark Harris, the founder of Gpgpu.org, coined the term Gpgpu. OpenVideo was developed at University of Toronto during 2003 to 2005, in collaboration with NVIDIA. Microsoft introduced the GPU computing language F, and the Direct Compute GPU computing API, released with the DirectX 11 API. MATLAB supports Gpgpu acceleration using the Parallel Computing Toolbox and MATLAB Distributed Computing Server, as well as third-party packages like Jacket. Gpgpu processing is also used to simulate Newtonian physics by physics engines, and commercial implementations include Havok Physics, FX and PhysX, both of which are typically used for computer and video games. Close to Metal, now called Stream, AMD ATI's Gpgpu technology for ATI Radeon-based GPUs. C++ Accelerated Massive Parallelism is a library that accelerates execution of C++ code by taking advantage of the data parallel hardware on GPUs. Mobile computers due to a trend of increasing power of mobile GPUs, general-purpose programming became available also on the mobile devices running major mobile operating systems. Google Android 4.2 enabled running render script code on the mobile device GPU. Apple introduced a proprietary Metal API for iOS applications, capable of executing arbitrary code through Apple's GPU compute shaders. Hardware support. Computer graphics cards are produced by various vendors, such as NVIDIA and AMD ATI. Cards from such vendors differ on implementation of data format support, such as integer and floating point formats. Microsoft introduced a shader model standard, to help rank the various features of graphic cards into a simple shader model version number. Integer numbers pre-DirectX 9 graphics cards only supported paletted or integer color types. Various formats are available, each containing a red element, a green element, and a blue element. Sometimes an additional alpha value is added, to be used for transparency. Common formats are 8 bits per pixel sometimes palette mode, where each value is an index in a table with a real color value specified in one of the other formats. Sometimes 3 bits for red, 3 bits for green, and 2 bits for blue. 16 bits per pixel usually allocated as 5 bits for red, 6 bits for green, and 5 bits for blue. 24 bits per pixel 8 bits for each of red, green, and blue, 32 bits per pixel 8 bits for each of red, green, blue, and alpha. Floating point numbers for early fixed function or limited programmability graphics. This was sufficient because this is also the representation used in displays. This representation does have certain limitations, however. Given sufficient graphics processing power, even graphics programmers would like to use better formats, such as floating point data formats, to obtain effects such as high dynamic range imaging. Many Gpgpu applications require floating point accuracy, which came with graphics cards conforming to the DirectX 9 specification. DirectX 9 Shader Model 2X suggested the support of two precision types, full and partial precision. Full precision support could either be FP32 or FP24 or greater, while partial precision was FP16. ATI's A300 series of GPUs supported FP24 precision only in the programmable fragment pipeline, while NVIDIA's NV30 series supported both FP16 and FP32. Other vendors such as S3 Graphics and XGI supported a mixture of formats up to FP24. Shader Model 3.0 altered the specification, increasing full precision requirements to a minimum of FP32 support in the fragment pipeline. ATI's Shader Model 3.0 compliant R5XX generation supports just FP32 throughout the pipeline, while NVIDIA's NV4X and G7X series continued to support both FP32 full precision and FP16 partial precisions. Although not stipulated by Shader Model 3.0, both ATI and NVIDIA's Shader Model 3.0 GPUs introduced support for blendable FP16 render targets, more easily facilitating the support for high dynamic range rendering. The implementations of floating point on NVIDIA GPUs are mostly IEEE compliant. However, this is not true across all vendors. This has implications for correctness which are considered important to some scientific applications. While 64-bit floating point values are commonly available on CPUs, these are not universally supported on GPUs. Some GPU architectures sacrifice IEEE compliance while others lack double precision altogether. There have been efforts to emulate double precision floating point values on GPUs. However, the speed trade-off negates any benefit to offloading the computation onto the GPU in the first place. Vectorization most operations on the GPU operate in a vectorized fashion. One operation can be performed on up to 4 values at once. For instance, if one color is to be modulated by another color, the GPU can produce the resulting color in one operation. This functionality is useful in graphics because almost every basic data type is a vector. Examples include vertices, colors, normal vectors, and texture coordinates. Many other applications can put this to good use, and because of their higher performance, vector instructions have long been available on CPUs. GPU versus CPU. Originally, data was simply passed one way from a CPU to a GPU, then to a display device. However, as time progressed, it became valuable for GPUs to store at first simple, then complex structures of data to be passed back to the CPU that analyzed an image, or a set of scientific data represented as a 2D or 3D format that a graphics card can understand. Because the GPU has access to every draw operation, it can analyze data in these forms very quickly, whereas a CPU must poll every pixel or data element much more slowly, as the speed of access between a CPU and its larger pool of random access memory is slower than GPUs and graphics cards, which typically contain smaller amounts of more expensive memory that is very much faster to access. Transferring the portion of the data set to be actively analyzed to that GPU memory in the form of textures or other easily readable GPU forms results in speed increase. The distinguishing feature of a Gpgpu design is the ability to transfer information bidirectionally back from the GPU to the CPU. Generally, the data throughput in both directions is ideally high, resulting in a multiplier effect on the speed of a specific high-use algorithm. Gpgpu pipelines may improve efficiency on especially large datasets and/or data containing 2D or 3D imagery. It is used in complex graphics pipelines as well as scientific computing. Particularly in fields with large datasets like genome mapping, or where 2- or 3-dimensional analysis is useful, in particular at present biomolecule analysis, protein study, and other complex organic chemistry. Such pipelines can also vastly improve efficiency in image processing and computer vision, among other fields, as well as parallel processing generally. Some particularly heavily optimized pipelines have yielded speed increases of several hundred times the original CPU-based pipeline on one high-use task. A simple example would be a GPU program that collects data about average lighting values as it renders a particular view from either a camera or a computer graphics program back to the main program on the CPU, so that the CPU can then make adjustments to the overall screen view. A more advanced example might use edge detection to return both numerical information and a processed image representing outlines to a computer vision program controlling, say, a mobile robot. Because the GPU has fast and local hardware access to every pixel or other picture element in an image, it can analyze and average it or apply a Sobel edge filter or other convolution filter with much greater speed than a CPU, which typically must access slower random access memory copies of the graphic in question. Gpgpu is fundamentally a software concept, not a hardware concept. It is a type of algorithm, not a piece of equipment. However, specialized equipment designs may even further enhance the efficiency of Gpgpu pipelines, which traditionally perform relatively few algorithms on very large amounts of data. Massively parallelized, gigantic data-level tasks thus may be parallelized even further via specialized setups such as rack computing, which adds a third layer, many computing units each using many CPUs to correspond to many GPUs. Some Bitcoin miners use such setups for high-quantity processing. Caches equals, historically, CPUs have used hardware-managed caches but the earlier GPUs only provided software-managed local memories. However, as GPUs are being increasingly used for general-purpose applications, state-of-the-art GPUs are being designed with hardware-managed multi-level caches which have helped the GPUs to move towards mainstream computing. For example, GT200 architecture GPUs did not feature an L2 cache, the Fermi GPU has 768 KB last-level cache, the Kepler GPU has 1536 KB last-level cache, and the Maxwell GPU has 2048 KB last-level cache. Energy efficiency equals, Several research projects have compared the energy efficiency of GPU with that of CPU and FPGA. Stream processing. GPUs are designed specifically for graphics and thus are very restrictive in operations and programming. Due to their design, GPUs are only effective for problems that can be solved using stream processing, and the hardware can only be used in certain ways. The following discussion referring to vertices, fragments and textures concerns mainly the legacy model of Gpgpu programming, where graphics APIs were used to perform general-purpose computation. With the introduction of the CUDA and Opencl general-purpose computing APIs, in new Gpgpu codes it is no longer necessary to map the computation to graphics primitives. The stream processing nature of GPUs remains valid regardless of the APIs used. GPUs can only process independent vertices and fragments, but can process many of them in parallel. This is especially effective when the programmer wants to process many vertices or fragments in the same way. In this sense, GPUs are stream processors or processors that can operate in parallel by running one kernel on many records in a stream at once. A stream is simply a set of records that require similar computation. Streams provide data parallelism. Kernels are the functions that are applied to each element in the stream. In the GPUs, vertices and fragments are the elements in streams and vertex and fragment shaders are the kernels to be run on them. Since GPUs process elements independently, there is no way to have shared or static data. For each element we can only read from the input, perform operations on it, and write to the output. It is permissible to have multiple inputs and multiple outputs, but never a piece of memory that is both readable and writable. Arithmetic intensity is defined as the number of operations performed per word of memory transferred. It is important for Gpgpu applications to have high arithmetic intensity, else the memory access latency will limit computational speedup. Ideal Gpgpu applications have large data sets, high parallelism, and minimal dependency between data elements. GPU programming concepts equals computational resources. There are a variety of computational resources available on the GPU. Programmable processors are vertex, primitive, fragment and mainly compute pipelines allow programmer to perform kernel on streams of data. Rasterizer creates fragments and interpolates per vertex constants such as texture coordinates and color. Texture unit read-only memory interface. Frame buffer write-only memory interface. In fact, the programmer can substitute a write-only texture for outputs instead of the frame buffer. This is accomplished either through render to texture, render to back buffer copy to texture, or the more recent stream out. Textures as stream. The most common form for a stream to take in Gpgpu is a 2D grid because this fits naturally with the rendering model built into GPUs. Many computations naturally map into grids, matrix algebra, image processing, physically based simulation, and so on. Since textures are used as memory, texture lookups are then used as memory reads. Certain operations can be done automatically by the GPU because of this. Kernels can be thought of as the body of loops. For example, a programmer operating on a grid on the CPU might have code that looks like this. On the GPU, the programmer only specifies the body of the loop as the kernel and what data to loop over by invoking geometry processing. Flow control. In sequential code it is possible to control the flow of the program using if-then-else statements and various forms of loops. Such flow control structures have only recently been added to GPUs. Conditional writes could be accomplished using a properly crafted series of arithmetic bit operations, but looping and conditional branching were not possible. Recent GPUs allow branching, but usually with a performance penalty. Branching should generally be avoided in inner loops, whether in CPU or GPU code, and various methods, such as static branch resolution, pre-computation, predication, loop splitting, and zcul can be used to achieve branching when hardware support does not exist. GPU methods equals map. The map operation simply applies the given function to every element in the stream. A simple example is multiplying each value in the stream by a constant. The map operation is simple to implement on the GPU. The programmer generates a fragment for each pixel on screen and applies a fragment program to each one. The result stream of the same size is stored in the output buffer. Reduce. Some computations require calculating a smaller stream from a larger stream. This is called a reduction of the stream. Generally, a reduction can be accomplished in multiple steps. The results from the prior step are used as the input for the current step, and the range over which the operation is applied is reduced until only one stream element remains. Stream filtering. Stream filtering is essentially a non-uniform reduction. Filtering involves removing items from the stream based on some criteria. Scan. The scan operation, also known as parallel prefix sum, takes in a vector of data elements and an associative binary function plus with an identity element I. If the inputs is A0, A1, A2, A3, an exclusive scan produces the output I, A0, A0 plus A1, A0 plus A1 plus A2. While an inclusive scan produces the output A0, A0 plus A1, A0 plus A1 plus A2, A0 plus A1 plus A2 plus A3. While at first glance the operation may seem inherently serial, efficient parallel scan algorithms are possible and have been implemented on graphics processing units. The scan operation has applications in, for example, quicksort and sparse matrix vector multiplication. Scatter. The scatter operation is most naturally defined on the vertex processor. The vertex processor is able to adjust the position of the vertex, which allows the programmer to control where information is deposited on the grid. Other extensions are also possible, such as controlling how large an area the vertex affects. The fragment processor cannot perform a direct scatter operation because the location of each fragment on the grid is fixed at the time of the fragment's creation and cannot be altered by the programmer. However, a logical scatter operation may sometimes be recast or implemented with an additional gather step. A scatter implementation would first emit both an output value and an output address. An immediately following gather operation uses address comparisons to see whether the output value maps to the current output slot. Gather. This method is the reverse of scatter. After scatter reorders elements according to a map, gather can restore the order of the elements according to the map scatter used. Sort. The sort operation transforms an unordered set of elements into an ordered set of elements. The most common implementation on GPUs is using radix sort for integer and floating point data and coarse-grained merge sort and fine-grained sorting networks for general comparable data. Search. The search operation allows the programmer to find a particular element within the stream, or possibly find neighbors of a specified element. The GPU is not used to speed up the search for an individual element, but instead is used to run multiple searches in parallel. Mostly the search technique used is binary search on sorted elements. Data structures. A variety of data structures can be represented on the GPU: dense arrays, sparse arrays, static or dynamic, adaptive structures. Applications. The following are some of the areas where GPUs have been used for general-purpose computing: computer clusters or a variation of a parallel computing for highly calculation-intensive tasks. High-performance computing clusters, including cluster technologies like message passing interface, and single-system image, distributed computing, and Beowulf. Grid computing, load balancing clusters. Physical-based simulation and physics engines, Conway's Game of Life, cloth simulation, incompressible fluid flow by solution of Euler equations or Navier-Stokes equations. Statistical physics, Ising model. Lattice gauge theory, segmentation, 2D and 3D, level set methods, CT reconstruction, fast Fourier transform, GPU learning, machine learning and data mining computations, for example with software BID match, K-nearest neighbor algorithm, fuzzy logic, tone mapping, audio signal processing, audio and sound effects processing, to use a GPU for DSP, analog signal processing, speech processing. Digital image processing, video processing hardware, accelerated video decoding and post-processing, motion compensation, inverse discrete cosine transform, variable length decoding, inverse quantization, in-loop deblocking, bitstream processing using special-purpose hardware for this task because this is a serial task not suitable for regular Gpgpu computation, deinterlacing, spatial temporal deinterlacing, noise reduction, edge enhancement, color correction, hardware accelerated video encoding and pre-processing, global illumination ray tracing, photon mapping, radiosity among others, subsurface scattering, geometric computing constructive solid geometry, distance fields, collision detection, transparency computation, shadow generation, scientific computing, Monte Carlo simulation of light propagation, weather forecasting, climate research, molecular modeling on GPU, quantum mechanical physics, astrophysics, bioinformatics, computational finance, medical imaging, computer vision, digital signal processing/signal processing, control engineering, operations research, implementation of the GPU taboo search algorithm, solving the resource-constrained project scheduling problem is freely available on GitHub. Neural networks, database operations, lattice-Boltzmann methods, cryptography and cryptanalysis, performance modeling, computationally intensive tasks on GPU, implementation of MD6, implementation of AES, implementation of DES, implementation of RSA, implementation of ECC, password cracking, cryptocurrency transactions processing, electronic design automation, antivirus software, intrusion detection, increase computing power for distributed computing project like SETI at home, Einstein at home. Bioinformatics Gpgpu usage in bioinformatics. Molecular dynamics. Expected speedups are highly dependent on system configuration. GPU performance compared against multi-core x86 CPU socket. GPU performance benchmarked on GPU-supported features and may be a kernel-to-kernel performance comparison. For details on configuration used, view application website. Speedups as per NVIDIA in-house testing or ISV's documentation. Q equals Quadro GPU, T equals Tesla GPU. NVIDIA recommended GPUs for this application. Please check with developer/ISV to obtain certification information. See also, Graphics Processing Unit, Opencl, OpenMP, OpenACC, OpenHMPP, Fastra2, Stream Processing, Mark Harris, Physics Engine, Advanced Simulation Library, Physics Processing Unit, Havoc Physics, FX, PhysX. Close to Metal, C++ AMP, Direct Compute, RenderScript, Audio Processing Unit, Larrabee. References. External links, openhmpp.org, a new open standard for many core, Opencl tools, open source, Opencl compiler and linker, gpgpu.org, a general purpose computation using graphics hardware, Gpgpu wiki, SIGGRAPH 2005 Gpgpu course notes, IEEE Vista 2005 Gpgpu course notes, NVIDIA Developer Zone, AMD GPU tools, CPU versus Gpgpu, what is GPU computing? Tech Report article, ATI stakes claims on physics, Gpgpu ground by Scott Wasson, GPU accelerated Monte Carlo simulation of the 2D and 3D Ising model, porting a standard model to GPU hardware, Gpgpu computing at Duke Statistical Science, Gpgpu programming in F using the Microsoft Research Accelerator System.